Good afternoon. I want to thank the organizers for putting the paper on the program. This is joint work with Darrell Duffie called size discovery. Let me first explain what we mean by size discovery by explaining the difference between size discovery and price discovery. By price discovery, we typically refer to the fact that financial market, the price in the financial market aggregates information. So we could have different information, different inventory shocks, different hedging need, and all of those would come into our demand and supply when we trade in the financial market. By equaling demand and supply, the market clearing price is going to reveal sort of the average information, inventory shock, etc. Now, size discovery is very different. It says, let's think about a different way, right? Forget about the market clearing for a moment. Let's just give you a price, and let's try to find out how many shares or how many quantity of asset could the buyers and sellers exchange at this given price. Now, you might wonder, why is that useful? Isn't the market clearing the sort of the fundamental property of the financial market? So in this paper, we are going to argue that a careful market design that combines size discovery with price discovery is going to deliver a pretty good improvement in the allocation efficiency. So here is a one-figure illustration of the main idea. Suppose we are right here, and this allocator, this is price, sort of the two fundamental properties or two fundamental functions of financial market. We're trying to get to there, right? Given the current information that we do not reveal for now, we try to get this is the correct price and the correct allocation. In a competitive market, we could typically do that in one go, right? People would submit demand schedules or orders that says you are willing to trade. How much you're willing to trade is such that your marginal value is equal to the price, and we can go to there in one go. Now, in actual market, because people are sensitive to price impact and there is not perfect competition, what's going to happen is that we are not going to achieve the best allocation. Typically, we cannot go there. But in many situations, we could still achieve the best price. So in other words, price is not sacrificed, but allocation is sacrificed if there are frictions like this. Now, where does size discovery come in? Size discovery works entirely on the dimension of allocations. I just give you the old price, say yesterday price. That's typically an incorrect price or sort of the wrong price. But for now, it doesn't matter. Let's try to figure out how many shares we could exchange at this price. Typically, we could have a non-trivial volume. Now, if you combine price discovery and size discovery sort of in the right way, we can deliver a allocation profile that is much closer to where we're going to than having price discovery alone. So for the rest of the time, I'm going to go through some of the details about how size discovery works in practice and show you the model and basically some empirical predictions and welfare implications. Now, at the general motivation, the idea of price impact is important for any large investor and a large intermediary. That applies to all the market, from the very illiquid ones like bond markets to the very liquid ones like stocks market. And there's a recent discussion about runs on illiquid funds, etc. These also come from the fact that trades create temporary price impact. And people blamed on many things: technology advancement and regulation. In fact, I'll show some of these properties that in a very speedy, fast market, we could have even a higher price impact. Now, how do investors mitigate the price impact? Imagine that you're asset manager, you try to liquidate 1 million shares today, okay? You're not going to dump the whole thing into the market because that's going to drive the price way down. Instead, you probably would gonna put some orders into the open auction in the stock exchanges and gradually work your way down. Now, this way is fully rational, and that saves you price impact, right? But it is also slow and gradual. You can see that you are still not at your ending or target inventory. So the space between your actual inventory and your target inventory could be thought about as a measure of how inefficient the allocation is. We'll make it a form, of course. As an interesting fact, I think the average trade size in the US equity market is only 100 or 200 shares, even though the total volume is huge, right? The order splitting these days is just tremendous. Now, this is the figure shown with the buyer and the seller. That's even more obvious. You can see that the seller and the buyer both try to trade a big quantity, 1.5 million, 2 million, but because of the price impact, they both try to do a lot of order splitting, and therefore the convergence of allocation is very slow and gradual. The white space between them sort of, again, is a measure of the inefficiency. Now, here is where size discovery could come in and be helpful. Again, the fundamental idea of size discovery is that we shut down price discovery for now, for a moment. Forget about market clearing. Instead, we can try to get a block trading by trading at the fixed price. The idea is that if the allocation inefficiency is due to the strategic avoidance of price impact, then by fixing the price, then nobody would worry about pushing the price around anymore, right? And in fact, in financial market, there are many examples that size discovery plays along. Today, I'm going to focus on the first one, which is the workup protocol in treasury market. But there are many other ones, such as matching sessions and the dark pools. The dark pool one probably has the most profile because that's in equity market. Here's roughly how it works. According to the recent New York Fed study, the workup protocol accounts for about 50% of trading volume for on-the-run treasuries. The on-the-run treasury market is kind of an electronic market. It's an order book. How it works is the following. Think about this order book, and one trade happens on the order book. Instead of continuing trading on the order book gets frozen for a few seconds. So suppose the last price is P, let's say 102 per 100. Then additional buyers and sellers are invited to submit orders at the same price, the fixed price P. Now, in that process, the price cannot move. Okay, it's frozen. Right? So in that sense, it is a size discovery mechanism. Imagine that 3 buyers and 4 sellers would queue up. Now, how does this work? Once the first buyer and the first seller, they meet. They don't literally see each other, but electronically they kind of meet on the platform, and they are going to increase the size of their trading volume continually unless one of them wants to jump out. You can imagine that there is an invisible dial going from 0 to the right very fast. Whenever one side decides to quit, the other side, the next one would jump in. Okay? So once all of these orders are exhausted, in this case, all the sellers are done, but the buyers still have something left. In other words, market doesn't clear. If nothing happens after 3 seconds, then the order book resumes. So what happens is that there is a price, and then we're going to trade at fixed price. Now, here are some other examples, but in the interest of time, let me just highlight this one. In the derivative market, Colin Dufresne and the co-author, they find that on this particular trading platform, GFI, which is the interdealer platform for index CDS, over 70% of volume is done through a workup-like protocol. Okay, so this is an important one for large trades. In equities, of course, we get block crossing dark pools like Liquidnet and Deposit. Okay. Now, let me spend a minute on these slides because they sort of shows the main ideas here. Again, the 2 thin lines are the inventory path of a buyer and a seller who only engage in this price discovery mechanism. Again, that's a slow convergence, very smooth. People worry about the price impact. Let's consider the alternative market design by adding one single workup at the beginning. Okay, one single round of size discovery before we all go to the order book or auctions. Now what's going to happen? Because the buyer and the seller no longer worry about the price impact at the fixed price, they are willing to disclose more of their trading interest. As a result, a lumpy reduction in the inventory imbalance takes place. Okay? So that's going to deliver a robust improvement in allocation efficiency. So the 2 curves, that is solid and thick curves, is much closer together, right? So you can imagine that these 2 areas white space is the amount of allocation efficiency that is improved by adding size discovery. Now that's the first point. Now the second point is that you see that neither the seller nor the buyer would go all the way down to 0. Now this is due to a winner's curse problem. Imagine that you are right here, you are the seller. If you keep selling until you have a 0 inventory, what's your inference about the buyer's inventory? The buyer is willing to trade at the fixed price. That means the buyer's inventory probably is larger. What does that mean about subsequent auction prices, order book prices? It's probably going up, right? Therefore, as a seller, you don't want to liquidate everything, right? Instead, you want to self-ration, reserve some quantity to be executed at a later date when the price is expected to be better. So, of course, the buyer would do the same calculation. As a result, both sides would actually do some self-rationing. The important practical implication of this kind of behavior, winner's curse, is that size discovery is not useful for small traders. Retail investors almost certainly do not want to use them. You want to use them only if you're big, right? You have large quantities. And even if you're a large dealer, if you have a small realization of inventory imbalance, you do not want to use them. Okay, lastly, I want to mention that size discovery by itself is not a panacea. If you only choose one mechanism, you would rather choose price discovery. What we are trying to say is that having the linear combination, the right combination between the 2 is better than the corner solution of having only one. Okay. Not a lot of literature on size discovery. The only theory paper we are aware of is the Panks. He shows how size discovery by gradually disclosing trading interest prevents front running. I have early work on dark pools, but that is entirely orthogonal because that paper is on price discovery instead of size discovery. And here are some empirical papers. There are some early papers on treasury market and workup. There are some recent ones given the current debate about the market structure in treasury market and in swaps. Okay, so for the remaining of the time, since I have elaborated the main intuition, I'm going to show you a taste or the flavor of how the model works and discuss the sort of the formal theorem behind it, as well as the empirical and the policy implications. The first then is to show a simple model with price discovery alone, right? That is sequential batch auction model. And then we'll see what happens if we add in this size discovery mechanism. I'll probably skip the multi-letter workup in the interest of time. So the sequential batch auction model is based on my earlier work with Du. It's a very simple one. Imagine that each one of us in the room is a strategic trader. There are like n of them. The key point is that n is finite, right? That's the only thing that's needed. And we all care about price impact. The asset is assumed to be extremely simple. We all have symmetric information about the asset value. In particular, the asset value is going to be realized at some future date called t. And that future date follows some exponential distribution with intensity r. Once that asset value is realized, we all basically get the dividend and go home. The expected value of the asset is v. Now, one way to think about this setup is that each one of us is the investor or the dealer, say in the treasuries market, and the future liquidation date is when the Federal Reserve decides to raise the interest rate again, because that's the sort of a date when all of the values are hit, okay? Now, before pi, this value is realized, each one of us is going to incur a quadratic holding cost. This is meant to capture the fact that we don't like holding inventory ahead of this big important announcement, okay? It's quadratic because the first order condition would be linear. That's keep it attractable. In addition, we are going to receive inventory shocks. Imagine in the beginning of the day, we wake up, we receive inventory shocks from customers overnight. Okay? Now, those inventory shocks needs to be rebalanced, and that introduces gain from trade. In addition, during the day, we also receive periodic inventory shocks denoted by W. Now, those periodic inventory shocks are actually not needed for the model, but it is very useful to eliminate some multiple equilibrium. Now, the trading protocol is a very simple batch auction model, a sequential batch auction model. Almost it's like a sequential Grossman-Stiglitz type. The model is that we all get together and submit the demand schedules, and the market is going to clear. In particular, each pair of double auctions is sort of spaced out by time delta. You can think about the delta is how speedy, how fast the market is. High frequency market is when delta is close to 0. Okay? Now, the demand schedule in each auction says at the price P, trader I is willing to buy this quantity. Of course, if that quantity is negative, then that means a sell, right? Price clears the market by setting this to 0. Now, let me just describe the intuition of why in this market, allocation is not efficient. Remember, there are only n of us, and we are strategic. If we were competitive, we would submit the demand schedules that look like the blue lines, okay? So the blue lines imply that the price is equal to the marginal value. So we're going to cross at this price. But because we are strategic, we worry about pushing the price away from us. So we are going to strategically understate how much we are willing to buy or sell. If I'm a buyer, I'm certainly not going to tell them my true quantity. I'll understate it, and therefore pushing the price in my favor. So what's going to happen is that buyers and sellers both make their demand curve flatter, and that is shown at the two dotted lines. In this particular example and in this model, the price stays the same, but how much allocation of asset takes place at the price is much lower. You can see it's here instead of here, right? Now, this is the source of inefficient allocation when people take into account about price impact, and they try to avoid them. Now, more formally, the demand schedule has a simple form. It is a constant A times V minus P, the value minus the price, minus the constant times the inventory. If you have a lot of inventory already, you certainly don't want to buy a lot. And this parameter A can be solved in explicit form. We don't have to worry about this, but basically this A is smaller than this leading term. The price P aggregates the information in the market. In this case, because we have a symmetric information about V, the only asymmetric information is really the total inventory all of us hold on this asset. An interesting property I want to mention now is that A, this leading multiplier, gets really, really small if you are in a very fast market. The intuition is that if you can trade in the next millisecond, how willing are you to suffer price impact? The answer is not much. Therefore, your demand schedule is really, really flat. Okay? So this is sort of corresponds to the very small order size in a very fast market. Of course, as n goes to infinity, this A would go to the competitive equilibrium. Now again, this is the inventory path solved by pushing delta to 0. because the model is fully tractable, we can in fact write down the evolution of inventories as well as the continuation value. So the evolution inventory goes like this. How much I am in this round from my efficient allocation is equal to how far I was in the last round multiplied by constant times plus a inventory shock. All of those could be integrated out, right, because that's all in closed form. Standing at the time 0 after the first double auction that reveals the initial total inventory size, I could write down my continuation value as a function of my current inventory, initial inventory, as this term. Now, these two terms says if we were to hold the efficient allocation in the beginning, that's how much we would get, right? V times quantity minus holding cost. The second term says if I were able to sell my excess inventory at the market clearing price, this is how much I get. But because I'm so strategic, I'm not going to sell all of my excess inventory in one go, right? Therefore, there's a quadratic drag. The quadratic drag measures the inefficient allocation due to this strategic avoidance of price impact. So the whole game here is try to minimize this term as much as possible. And the final term simply takes into account the expectations of all these periodic inventory shocks, which is a constant, okay? So that's pretty much the last slide of this simple benchmark model. So what we're going to do is to take this as a continuation value and then try to add one round of workup before it. Are you okay with that? Yeah. Now, to fix the ideas and for simple intuition, we are going to add one round of bilateral workup. Namely, we just pick one buyer and one seller, let both guys try to determine how much they could trade. The workup price is fixed exogenously. One way to think about this price is the old price, yesterday's closing price, or maybe the average price during today's trading. But the key thing is that doesn't move. We assume that the buyer and seller both have the inventory size that have an exponential distribution. The parameters don't need to be the same, but it simplifies the calculation. Their mean is 1 over mu. Now, the trading protocol is that they both hold down the button, right? As long as the buttons are held down, the quantity is going to increase from 0 to the right. As soon as one of them lifts the finger, the workup will finish. In that case, both parties would go to the double auctions together with anyone who did not participate in workup. In other words, the participation into size discovery does not prevent you from participating in the double auctions, right? So size discovery is more of an increment market. Now, what's the trade-off here? In order to find out, right, what's the efficient allocation, we sort of need to find out exactly the strategies. And the key property that determines the strategy is this trade-off. Now, imagine that you're the seller, and you already did some workout with the buyer, and your decision right now is whether to trade additional million, right, additional quantity. There are two effects. On the one hand, you probably would want to sell this additional quantity because if you were stuck with it, it takes you a while to liquidate. So in the meantime, that incurs holding cost. On the other hand, there's a cost of winner's curse, right? As I said before, if you are really close to 0, you'd imagine, gosh, the buyer is probably big, therefore maybe I should withhold this additional quantity because the price in the double auction 1 instant later is going to be better. So as a seller, you start way out there. As you work your way down, you see the cost become higher and higher, whereas the benefit becomes smaller and smaller. At one point, cost equals benefit, therefore you're going to drop out of the workup. The buyer, of course, has the same calculation. So the equilibrium would have the following shape. The seller would set an endogenous threshold when the seller drops out, and the buyer does the same. So in equilibrium, both parties would start way out and walk in toward each other at the same speed until one of them hits one of these thresholds, right, and the workup would finish. Now, this game can repeat among many pairs. So we are here demonstrating how that works with one pair. Right? Okay, how am I doing on time? I would be happy to show you.
10 minutes.
Okay, I'll be happy to show you 3 pages of math if that is fine. But the reason I want to do that is that the 3 pages of math really illustrated my idea behind the theory. So I'll go through it if that's okay, right? Now, imagine you're the buyer, right? How would you calculate when you want to stop out, okay? Now, you know that you start with the inventory as of B, and you just acquired quantity Y. Your termination value after the workup is going to be given by this script V function. But also, you're going to pay for it minus Py, okay? Now, you are trying to maximize your expected utility given the functional, the information that you learned once you liquidate quantity Y. Now, the tricky part, or the non-trivial part of it, is that as you liquidate more and more, this information starts to change, because that's going to change your expectation of your counterparty's inventory size. Now, exactly how does this work out? The information set consists of two parts. One is that your remaining inventory size is larger than how much your dropout threshold is. Otherwise, you have dropped out already. More importantly, your counterparty's, the seller's inventory size, SSS minus Y, is probably bigger than her inventory size, dropout inventory size. Okay? So once we substitute in, we see that the whole equation, there's many terms, but just focus on the two terms that involve the first moment and the second moment. All you care about, what is the expected value of the total inventory and what is the expected second moment. Now, for the expected total inventory, you know that everybody who did not participate probably would have average inventory of 0, so they would wash out. But between you, the buyer, and the seller, how much do you have together? You have S of B plus Y. You know that the seller has something more than M of S, but the conditional on exceeding M of S, because of Mermolli's property of exponential distribution, the mean is going to be 1 over mu. So this is where the exponential distribution comes in handy, right? So this whole thing becomes a constant right here. You can do the same thing with the second moment. That leads to a quadratic function of y, linear quadratic function of y. Okay. Now, once we substitute in both terms into this and it takes first order condition, because they are both linear quadratic in y, if you take a first order condition with y, you get a linear first order condition, right? That's basically what the linear first order condition looks like. And the final step is to say, well, because my optimal inventory size satisfies, I want to keep a minus FB. So by substituting this term into here, I should get 0. So this equation would give you a linear equation of M of B, your dropout threshold, and your counterparty dropout threshold, M of S. Now, of course, the seller does the same calculation, which is shown here. Two equations and two unknowns. Right? Now, the final solution is very simple. The dropout threshold, M of B, M of S, consists of a symmetric solution, M, and offset delta. The offset delta only depends on here. We can see this, how biased the price is. Now, of course, we do it for generality, but of course, in practice, the most natural price is going to be the expected value V. Right? Now, here's the figure again. In this model, we could actually calculate, given we solve the equilibrium, we could calculate exactly how big are these inventory collapse, right? Inventory imbalance reduction is sizable. In fact, we can further show that if we were to add in the different protocol at the very beginning, such as another round of auction, another round of auction is not going to do anything. Right? So in fact, the mix of a heterogeneous trading mechanism is very important. It's not only about adding one extra round. Right? You need to add in one extra round of mechanism that is different from this price discovery mechanism here. Right? In this model, because everything could be solved, we can calculate the expected value, the expected probability of having the workup, the expected volume, and expected welfare gain. Let me emphasize the third point. What is the expected welfare gain? Yeah. So here, in the denominator, I show, well, we put in the inefficiency cost caused by the strategic avoidance of price impact between the buyer and the seller. Right? Under some assumptions about the distribution of inventory size, that can be integrated out as a closed form. Now, in the numerator, we put in how much of that inefficiency cost is eliminated by having this one round of workup. So this ratio R is a proxy for how effective size discovery is in eliminating allocation inefficiency. In the continuous time limit, right, as delta goes to 0, this R has a very simple closed form solution. Right? For example, if you only have 3 traders in the market, which is not too unrealistic if you think about, say, very illiquid corporate bonds or muni bonds, about 63% of inefficiency could be eliminated by just adding one round of size discovery. As n goes to infinity, as interestingly, R doesn't converge to 0. It converges to asymptotically about 28%. The intuition is that, yes, as n goes to really large, all of us become almost competitive, but we are not fully competitive yet. So the thin slice of inefficiency can still be reduced by adding one round of workup. So this would suggest that this is actually a pretty robust mechanism, and it could be fairly sizable in market, especially in market where the number of participants is very small. Now let me talk about some empirical predictions. The first one is that workups or size discovery mechanisms are more likely to happen and handle higher volume if we are in a high frequency market. Now, high frequency market has this property that you can trade in the next second or next millisecond, so you're not willing to suffer any price impact. Therefore, we are all getting extremely strategic, right? Our demand schedule is really flat. And in those situations, the convergence to allocation is very slow and very inefficient. That's why adding the size discovery is the most useful. Now, how could we test it? Potentially, we could use speed upgrade of electronic platforms. Could be just one way of testing it. The second prediction is that if we look across asset classes with a smaller n, think about stock versus bond, right? The market with a smaller n would see a higher fraction of volume handled by size discovery, right? Which is kind of corroborates the earlier statistic that in treasury market around 50%, but in stock market tends to be smaller. Now that could potentially be tested by just looking across the different stocks or different bonds. And finally, if the public news that shocks everybody's value arrives really kind of far into the future, then we become really patient, right? That is when adding the size DR is most useful, because if we are patient, we are going to split the order into too many smaller pieces. And that could potentially be tested by looking at how far we are from scheduled information releases such as FOMC, earnings announcement, and the macroeconomic data releases. Okay. I'm going to skip this one on the discussion of Fleming and Nguyen. So let me show you just a couple slides on multilateral workup, just to show you the flavor of the idea. But the intuition is very similar. Multilateral workup is slightly more complicated because we have many people, right? And whenever you see you sort of sitting in the workup and trading with a counterparty, there's a probability that there's a queue behind him and there's a queue behind you, right? So you sort of need to take into consideration of what is expected inventory size of those of guys who are already left and those of guys who are still into the market, right, in the market. So with here, we make the assumption that the numbers of buyers and sellers are exponential. Once we make that assumption, everything becomes more tractable. The idea is similar. In fact, if you look at the form of the ultimate solution of the dropout threshold, they have the similar form. There is a symmetric solution. There is an offset term. Okay, I won't have time to go to the details, but this is actually tractable, although it involves a little bit of analysis. Okay, so let me wrap up. In this paper, we look at the size discovery mechanisms. This is broadly motivated by the fact that these mechanisms are used a lot in financial market. And we argue that they are used a lot and useful for investor intermediaries because they can mitigate this strategic avoidance of price impact. Price discovery mechanisms are good, but once people are strategic, they are too slow in reallocating asset. Therefore, the right combination of heterogeneous mechanisms in general could deliver better allocation. And we showed one example of this in the low frequency size discovery. Of course, there are different ways of dealing with this by mitigating strategic avoidance of price impact. One example is by varying how frequently we hold these type of auctions, right? Trading the kind of varying the speed of the market. That is a separate paper I did with Stu. And the ultimate question of can we achieve the efficient allocation, the ultimate best allocation? That's a very difficult question, and we're going to leave that for future research. Okay, thank you.